Two objects are in a frictionless horizontal surface. One disk is initially moving to the right at a velocity v1 sub I, and disk 2 is spinning around its own center of mass at a angular frequency w2 sub I. Upon impact, they stick together as shown, so the center of the mass of disk 1 is on the outer radius of the disk 2. Disk 2, its center of mass is on an axle, which doesn't prevent any rotation, and it doesn't slow it down, but prevents any translation. The question is, what's the motion after impact? The radius of disk 1 is here, radius of disk 2 is here. When they impact, this offset is coming this direction, the offset is at D, and here's the masses of the two disks. So pause the video and we'll solve it and we'll check the answer. After the impact, the two-disk system is going to continuously rotate at this constant angular frequency in the final state, which is shown by this equation. Just check your answer out of that. If you got that answer, great. If you did, I'll go over how to get it. Starting to solve this problem, let's think of what the system would be. Well, it makes sense to pick disk 1 and disk 2 as my system and pick the surroundings of everything else. And now thinking about a free body diagram of the system, what forces are acting on any one of these disks? Now I'm going to draw it when it's in the coupled state. We're told that all the surfaces are frictionless, and looking from the top view, the only forces that are potentially acting are this axle. There could be some force on the x direction or in the y direction of the axle of the ground on the axle. Make more sense to draw this one this way. Okay, so the only forces acting on this plane are forces the board, and from the side view there'd be gravitational forces acting, but for right now we're worried about rotation in this plane, so we're not be concerned about those forces because vectorially they won't affect it. So I have forces acting on it, and we're worried about rotation, and ideally I'd like to try to get it so I can look at a point where the net torque is 0. So from the net torque of forces acting on my system, how can I get that to be 0? Well, I can get that to be 0. The forces have magnitude, so I might have some force. So I get that to be 0 if my r vector can be magnitude 0 length. And forces acting on this axle would go through that point, so the r vector magnitude length would be 0. So for anything where it's fixed, rotating about a point, it makes so much sense to pick the point that you're going to determine torques around, and therefore angular momentum around, is to pick the fixed point, because we know that these the forces of that fixed point due to the axle, those torques result of that is 0. And since those are the only forces acting on my system in this view, I know that the net torque around the center of disk 2 in this pick a coordinate system, call it x, y, and z's out of the board. So in the z direction, anything that's going to cause a torque in the z direction from the top view, well, I know that's going to be 0 if I pick that to be my point. So pick the center of the disk 2 as my point. Angular momentum is always about a point. So angular momentum with respect to time in the z direction is the net torque around this point in the z-axis. It's not z direction, not the z-axis, z direction. And we just said that's 0. So therefore, if the change is over time is 0, then this value is a constant. And if it's a constant, then I can consider in the z direction around this point, the center of disk 2, I have two elements to this system, the disk 1 and disk 2. So angular momentum initially is a translational rotational part of disk 1 and translational part and rotational part of disk 2 initially, and then the same thing finally. So if you didn't get to this point, pause the video and let's try to solve from here. Now starting putting in values. First one, the angular momentum rotationally of disk 1 about its own center of mass in the z direction. Well, we're told that disk number 1 is not spinning relative to its own center of mass initially, so that's 0. Translational angular momentum of disk 1 around the center of disk 2 in the z direction initially. So that's up here. So that's r cross p, where r goes from this point which we chose to do everything about, the center of disk 2, to the center of mass. So disk 1 now considered to be a particle, just at its center of mass for any translational. So from here, r vector goes from there, from this point which we chose, to the center of mass of this disk 1, and p is gamma mv. We'll assume gamma is 1. So mass and then velocity come here. So r cross, so essentially it's r mass of disk 1 times r cross v. And r cross v is a magnitude of r, magnitude of v sine theta. So r going here, r cross v. So one of the first thing to do is to find out directionality. So r cross v, so going r to v is in the inward the board direction, which is a negative. So we know this value is going to be negative. And r v sine theta, theta the angle between, so the r sine theta is d. So we know this magnitude here is r cross v is the initial velocity times d, and we know it's negative. Always do the right hand rule to check to see sign. So we know this term turns out to be minus the mass of disk 1 times this distance d, which is we get from r cross v, times the magnitude of the initial velocity, which is this. So we'll substitute it in here. Next term, rotational of in the z direction of disk 2. Now disk 2 is assumed to be, it's not a particle, but it's the real part, so disk 2 about its own center. Well, I'm told disk 2 initially is rotating about its own center at this angular frequency. So let's see directionality. It's spinning this way. We're going to call that a positive, so we know the answer is going to be positive, and we know it's rotating, if something rotating about its own center is its moment of inertia about its center times its angular frequency. So that's this term right here. Translational of the center, now disk 2 is shrunk down to a particle at its center of mass. Initially, is there any translational element of this disk 2? Well, the center of mass of disk 2 is located at this point right here, so we know there's both r and the velocity are 0, so that's 0. Now looking at in the final state. So first one, rotational angular momentum of disk 1 in the final state relative to its own center of mass in the z direction. Well, I'm going to say that the whole system has angular frequency omega sub f, and it's going to be in this direction. And I kind of drew pictures of this disk that's here stuck here initially, and I'm going to say that it's stuck to this piece and it's going to be rotating with it. And if there's a little mark on it, you can kind of see that this mark is showing that this disk 1 is rotating relative to its own center of mass. So for when this whole assembly makes one revolution, this disk around its own disk 1 with regard to its own center of mass does one revolution. So it has the same angular frequency as this. So therefore, rotational angular momentum about its own center of mass is its own moment of inertia times its angular frequency, and that's positive. Next term, translational angular momentum about the center of the disk in the z direction finally. So once again, that's r cross p. Okay, what does r mean? R again means from this point we chose, the center of disk 2, to the center of the, now the particle is considered to be, this disk 1 now is considered to be a particle that has just translation. So we'll draw it at this point. So here r is going from this point to there. So there's r, and v, and the momentum term is related to velocity. So it's the gamma times mass times velocity. And if we're assuming that this is stuck to it and, and the whole system's rotating omega sub f, then its velocity is going to be magnitude whatever the radius times the angular frequency, because it's just spinning around, and the center of the mass of this part is staying at this constant distance r sub d from this point. So here's my term right here. So you can and you can see sine of theta is 0, and sine of theta is 90 degrees, so sine of theta is 1. So m times r, the magnitude of r is this magnitude from this point to that point, and the velocity is the radius of disk 2 times angular frequency final. So this the mass times rd squared times angular frequency. So I put that in here, and then once again check. Yes, that's a r cross v out of the board, positive. Next one, rotational angular momentum of disk 2 about its own center in the z direction. I'm assuming disk 2 is rotating this at this omega sub f, positive direction. So that's going to be the moment of inertia of the disk with respect to its own center times angular frequency. Next, take this disk 2, shrink it down to a particle at its own center of mass. What's its velocity relative, the center of the mass relative to this point, c sub d2? Well, 0. Also, the r is 0, so that becomes 0. So there's all my terms for angular momentum in the z direction about this center of disk 2 initially and finally. So now we can solve for the final angular frequency. You can see on this side that all these have an omega sub f term, so I can take that out, and then just replacing the moment of inertia about the center of a disk was 1/2 the mass of the disk times the radius disk squared. For hoop it'd be 1, but for these are both disks, so I can put it in there. And the same thing for disk 2, I can put that here, and for disk 2 put that here. And take this term, you can see this would be the numerator, and bring this over to the denominator, and that would be my answer, which I got before. You can also kind of see from this equation, so what if disk 2 wasn't initially spinning, and this term was 0, then this would be 0, and you can see that the angular frequency final would be proportional to how far off this disk hit d, and also proportional to the initial velocity.